All right, so today, section 8.3, we're going to take a look at trigonometric integrals. And what we're really going to be looking at is what happens when we have exponents of trig functions. That's what it's really going to amount to. Okay, exponents of trig functions is what we're going to be talking about. So first we're going to talk about what happens when we have exponents on sine and cosine. So if the power on sine is odd, okay, so a 3, a 5, a 7, so forth, you save one of them, so you don't change them, in order to make it du. And you convert everything else into cosines. If the power on cosine is odd, you do the same thing. You save one of the cosines for du, and you convert the rest into sine. And of course, we're going to do examples so you can see how these actually play out. And then, if we happen to have all even powers on sines and cosines, we make use of what's called a power-reducing formula. And this is one that you may have seen in trig. It's not used frequently, but it is a true statement. It's a relationship of double angles to squaring. So sine squared of x is 1 minus cosine 2x over 2, and cosine squared of x is 1 plus cosine 2x over 2. And then once you make that change, one of your trig functions will now have an odd power. So to convert an odd, to convert an odd power of cosine, you apply to number 2. After that, to convert to an odd power of cosine, and then you apply number 2. It turns things into cosines. So we definitely need an example because that all sounds very wordy. Gibberish is what I heard somebody say, yes. Almost like gibberish, right? We're going to turn things into different powers, and we're going to save something, and we're going to change something else, and what does that look like? We could see an integration by parts with this. Most of the time we're going to see u substitutions with these, okay? All right, so here we have the integral of the sine cubed of 2 theta square root cosine of 2 theta. And what you see is that you have a sine that has an odd power, okay? So taking a look back and thinking through these list of guidelines, where is that going to place us in this list of guidelines? Yeah, the very beginning, the odd power of sines, okay? Sine is odd, and exponent is odd, I should say. So what we're going to do is we're going to save one of these, and we're not going to manipulate it. All right, so we have sine cubed, and I want to leave one of the sines there, and I want to change so I'll just rewrite them separated first. So I have a sine 2 theta, and then I have a sine theta, sine 2 theta, and I have the square root of the cosine of 2 theta, d theta. So saving one of them means we're separating it, and I'm not going to change this piece. It's going to stay sine 2 theta. Okay, so what does it mean to change this? Because it said we're going to save one and convert the others to cosine. Well, what it's referring to is that there is a relationship between powers of sines and cosines. And what you'll remember is it looks something like this. Right? Pythagorean identity with cosine and sine squareds. So if I have sine squared, which I do, I can change this formula and I can express it as sine squared of theta equals what? 1 minus cosine squared of theta. And I don't have actually just theta in my problem. I have 2 theta. That doesn't really change anything. It just means that my angle is going to be 2 theta. So this is 1 minus the cosine squared of 2 theta. The sine 2 theta that I told you I was going to not change is left unchanged. And then we have the cosine of 2 theta right here, d theta. Okay, so far so good? We've manipulated it using a Pythagorean identity. All right, we're going to clean up what we have. We're not going to mess with the piece that we said we're going to save. This one is a standalone object, okay? So don't touch it. Everything else, though, we're going to try to clean up and combine. So in particular, we have a cosine of 2 theta over here underneath a radical. And we're going to distribute that through to the 1 and through to the cosine squared. So underneath the radical means we have power 1/2, right? That's cosine to the 1/2. So I'm going to write that way. So this is cosine to the 1/2 of 2 theta. Or if you prefer, some people don't like to see that written that way, you can write cosine of 2 theta and to the 1/2 out here. On the other piece, I have a subtraction, and then I have a squaring and a power 1/2. What's the exponent on that piece going to be? Yeah, 5/2. This is cosine of 2 theta to the 5/2. I was doing something with rational exponents like this in my Calc 1 class the other day, and I talked about the fact that basically it's 2.5, right? It's 2, and it's a 1/2. 2.5 is the same as 5/2. All of this still has a multiplication factor of the sine 2 theta that I did not change right here, d theta. We're not messing with that. Here's the beauty of what goes on. You guys know the relationship between sine and cosine. They're derivatives of each other, and you maybe have a negative thrown in there at different points, right? But that means that it's really nice to do u substitution when you've got sine and cosine in a problem. One of them is going to be u and the other one's going to be du. Agreed? The part that we left unchanged, we left it unchanged because we want it to be du. So the part that we're going to actually identify as u in this problem is the other part, in this case, cosine of 2 theta. So what is du if the u is cosine of 2 theta? Sine of 2 theta, I need one more thing. What's that? There will be a d theta, but there's something else missing. There's a 2, right? Why is there a 2? Why is this 2 sine 2 theta instead of just sine of 2 theta? There's a chain rule. Huh? Yes, sorry. I was worrying about the 2. You guys were worrying about the negative, perhaps. Sorry, I couldn't hear Hannah was saying there. I just knew she wasn't saying 2. Right? You weren't saying 2, weren't you? You were not saying a 2. Okay, sorry. I couldn't hear Nate saying a 2 either. You guys, be bold. Tell me what you think. It doesn't hurt anything if you're wrong, right? You guys are all friends. Okay. We have a negative. Yes, the derivative of cosine is negative sine. That's true. Where's the 2 come from again? Caleb, you were trying to tell me. The chain rule, right? We have an angle inside that's 2 theta, so we have to have times 2 because we've got the chain rule. Fantastic. So I don't really have a negative 2 in the problem, so I'm going to have a negative 1/2 at the beginning when I start to change this. So we're going to have negative 1/2. You know what? I'll just write it down at the bottom. I have a negative 1/2. The integral of what? What is going on now in the problem? Yeah, du. Exactly.
Couldn't we have combined the cosines before we switched to du?
Yeah.
Couldn't we have combined them? What do you mean by combined them?
Cosine of the 1/2 versus cosine of the 5/2 would be cosine of the negative 4/2 or so.
Would it?
It's like extortion.
I mean, okay, so if that's true, then that means we would be able to do that with the u's as well. Is u to the 1/2 minus u to the 5/2 u to the 4/2? I wish. That would be nice, right? It's like saying is x squared minus x equal to just, yeah. They're not like terms because they don't have the same exponent, so we can't combine them. It would be so friendly if we could, though. That would be wonderful. Unfortunately, yeah, not going to work. Okay, let me copy this one to the next slide. Oh, I lied. I'm out of space. Okay, let me do that differently then. Okay, I'll just make it smaller. I apparently didn't leave myself enough space. That's okay. All right, so from here, we are going to integrate. So what's the integral of u to the 1/2? You knew I was going to ask, right? What is it? You don't know? Yes, you do. You do too. 2/3 u to the 3/2. I've got a negative 1/2 on the outside still here, so let me put that in. How about the integral of u to the 5/2? U to the 7/2, right? Okay, so we're increasing the powers by 1, so 5/2 becomes 7/2. I would divide by 7/2, so it's multiply by 2/7. I need a plus c on here eventually, so I'll just put it in right now. I can clean that up with the 2 in the front, or the 1/2 in the front, right? So this 2 can cancel with each of these 2's. The negatives will just switch my signs, so in a very real sense, I now have 1/7 u to the 7/2 minus 1/3 u to the 3/2. Yeah, I just multiplied through by a negative. I just switched the order. I did. A couple of reasons why I kind of like writing them that way. I was intending to do so because I wanted my positive number in front of my negative number, but it actually works kind of nicely too because the larger exponent's in front of the smaller one, which is also a little bit more traditional. Am I done? I'm really close. I need to change them back into sines and cosines, right? Or whichever one it should be used. And which one do I need? Cosine. So this is 1/7 cosine of 2 theta to the 7/2 minus 1/3 cosine of 2 theta to the 3/2 plus c. Does it look like a 9? It kind of does look like a 9. Sorry, I had a sign wrong on my paper. I was fixing it. That's better, isn't it? Thank you so much. All right. So that's what it looks like to save a power of sine and then to manipulate after that. Okay. I gave myself 2 slides for this one. Okay. This one says, first of all, we've got alphas instead of thetas, but I think we can handle that, right? I'm not sure, not so sure today. This one has a cosine to the power of 4. So take a look back at those guidelines. Which guideline are we going to have to use in order for this one? Yeah, the third one, right? I wanted to show you an example of what happens when they're even, because if I show you another example, number 2, it's going to look just like number 1. Okay, you do the same thing. Number 3 is different. It says to make use of this fact that sine squared or cosine squared has this form, and this one is cosine to the power of 4, so we're going to use the second form right here. So we're going to be using this form. Now, you might be looking at that and saying, but Dr. Hans, we have a cosine to the power of 4, and that says cosine squared. Yeah, it means times itself, exactly. So that is exactly what we're going to do. All right, so taking a look at this, what we're going to do is we're going to recognize that this is the cosine. I'm going to do probably more steps than some of you need to see, but just, humor me. This is the cosine squared, or times itself, right? So we're going to replace cosine squared with what that function back on that other slide said it was equal to, which was what? Close. It was 2x, 2 times the angle. But what's our angle in this problem? 3 alpha. So when we double our angle, we're actually going to get 6 alpha here. And then we're going to square this. Okay, are you guys okay with that? Does everybody see where the 6 alpha came from? Whoops. Doubling the angle, right? And our angle was already 3 alpha, so now we've got an angle 6 alpha. Fantastic. All right, we're going to multiply this out. So the first thing I'd like to do is write a 1/4 in the front. Why do I have a 1/4 in the front?
I was going to say that it's like ish, but then you round it out.
What's wrong?
She's doing her physics. It's funny. She's doing her physics homework. She's like saying all the Greek letters. Like, she's like this W and then this A thing, this little fish thing.
I was like, it's just fish times theta.
Fish times theta. Gotcha.
Here it looks like an A though, unless you draw them out and then it looks like a
Yeah. Okay, does everybody see where the 1/4 came from? Yeah, squaring the bottom. Okay, good. If I multiply this out, I'm not going to actually write out the multiplication fact, but it would be foiling, correct? So I'm going to have 1 plus 2 cosine of 6 alpha plus cosine of 6 alpha squared d alpha. Is that okay? Because the denominator is a 2 and it's squared. So I just pulled the 1/4 in front instead of writing each of them over 4. Nate, you're looking at me like I just stepped off the boat. I'm good? Awesome. That was crazy. Huh? Everything is squared. So like this one, this 2 is squared, so that becomes a 4 that's out in front. When I square this on top, I have to multiply it by itself, so it's 1 plus this times 1 plus this.
Then the third line, the entire thing squared.
Yeah, this is each piece squared. So this piece was 1 squared, this is the middle term, and this is our last term squared. Yeah. Okay, are we good?
Yes.
Okay, this is 3 separate integrals now. Agreed? The first 2 pieces are simple to do. So if I were to distribute the 1/4 back through, if you don't like the 1/4 in front, you have the integral of 1/4 d alpha plus the integral of 1/2 cosine of 6 alpha d alpha. Those 2 pieces, I don't need any other fancy techniques of anything to do them. But I still have a even power of cosine at the end.
How'd you get 1/2? Oh, this one.
Yes. What do I do when I have an even power of cosine? I do it again. Yes, I do. So, yeah, I know. So I have 1 plus the cosine of what this time? 12 alpha, right? I'm doubling my angle over 2 d alpha.
And then you have to have the 1/4 in there too.
Yes, I still need a 1/4. Let me put the 1/4 right here. Thank you for reminding me. Okay, let's just do the integration on the first 2 pieces, and then we'll manipulate the last one because it's a little bit still messier. So 1/4 would be 1/4 alpha, right? So the 1/2 will be 1/2. What is the antiderivative of cosine? Sine, positive sine, of the 6 alpha, but then 6 is going to go where?
The beginning, so it's gonna make it the 1/2 3.
Not quite. What was that? You're getting closer. It's 1/6. Right? We're not taking a derivative, we're taking an antiderivative. So instead of multiplying by the, it's like the chain rule backwards, right? So instead of multiplying by the 6, we're going to divide by the 6. It's really a u substitution, we're just not writing it out. U equals 6 alpha, and then the derivative is 6, but there's not a 6, so we're dividing by the 6. If you need to see the u substitution for that, you can write it out, but it's actually just the chain rule reversed on that step. So we get a 1/6. So we're going to have a 1/12 in front, so we're going to have. And then I have a 1/8 integral of 1 plus cosine 12 alpha d alpha. I am definitely out of space, but I'm actually pretty close to done. Let me just shrink this instead of using a new slide.
You can split that one up as well.
Yep, you can. You're exactly right. Okay, so you could write this. This is what Nate's suggesting. 1/4 alpha. I've got 1/12 sine of 6 alpha. And then I have plus the integral of 1/8 d alpha plus the integral, and you don't have to separate it to actually write it this way, but if it helps you to see it, then by all means. 1/8 cosine of 12 alpha. Put the 1/8 inside or outside, it doesn't much matter. So I have 1/4 alpha plus 1/12 sine 6 alpha. What's next? 1/8 what? Oh, alpha, because this one has alphas in it, And I'm running out of space there again, so what? I don't need to be, though. All right, the last piece. The last piece. Okay, what do we have? 1/8, and then what? Sine of 12 alpha times a 1 over 12. Yes, it is. And I have plus c at the end. Okay, these pieces can also combine right here, right? 1/4 and 1/8. How much is that? 3/8. Good job, Seth. 3/8 alpha. Some of our brains think in fractions quicker than others, right? It's a true statement. All right, so I've got 3/8 of alpha plus 1/12 sine 6 alpha plus minus, I think. And what is it, 1/96 sine of 12 alpha plus c.
How did you get minus?
Because you integrate cosine
Oh, yeah.
of, right?
Was it supposed to be negative?
Isn't it?
I don't think so. I think it's supposed to be positive. Yep, it is positive. I was just doing what you guys told me to do. It's right in my notes. That counts for something, right? The last one had a sign error in my notes, and this one's actually not. Okay, any questions on it? Is it messy? A little bit messy, yeah. So this step 3 business over here on these guidelines, not so fun. Steps 1 and 2 aren't too bad. They really aren't. You can usually get those done in one step and cleaned up pretty quickly. But step 3 is messy. And it'd be even messier if this power had been, say, to the power 6. Agreed? Yes. Yes, Seth.
So on that fourth line where fourth line down, where you all this, you just do the rule 3 again to get that 1 plus cosine.
This one right here?
Yeah.
Yes, you do that rule again, exactly, because you've got an even power of cosine. Yeah, that's exactly right. All right, changing gears. We did sines and cosines. Now we're going to do secants and tangents. So we group sine and cosine. I mean, they're very friendly in the fact that they are each other's derivatives, which is, of course, very nice. But we also like to group them because they have a Pythagorean identity. There's a Pythagorean identity relationship between secant and tangent as well. Do you guys remember it? What is it? Okay, secant squared. What was it?
Isn't it secant squared x minus or equals 1 minus tangent squared?
I think it's 1 plus tangent squared of x. Does anybody have their paper to verify for us that we wrote it down right? That one's right. Jaden says yes, so we'll go with it. Okay, so you'll notice that step 1 feels a lot like the last problem. It tells you what to do in step 2 as well if there's an even or an odd exponent on one of these features. So it says if secant's power is even, we save as secant squared, and we convert the rest into tangent. And then if tangent is odd, we save as secant tangent and convert the rest to secants. The relationship, the reason this is happening is remember what the derivative relationships are. What's the derivative of secant? Secant tangent. And what's the derivative of tangent? Secant squared. So that's why we want a secant squared or a secant tangent left in the problem to let the du be equal to that. So that's what's going on guidelines 1 and 2.
So that's secant minus tangent on number 2.
No, it's secant tangent like beside each other multiplied. It's a secant tangent. They're hyphenating it as how they write it when they write it in the book. It's a hyphenation. Yeah. That's a good question. It does look like a subtraction sign. Agreed. All right, if there are no secants and the power of tangent is even, then you convert a tangent squared value into a secant squared value and you use the relationship that I wrote on the bottom of the screen. All right, we can change that. No problem. If you have the integral of plain old secant to a power, and the power is not even, right, like it's going to be odd, then you use integration by parts. And there it is. There's that integration by parts, your new favorite technique, right? With dv equal to secant squared. dv equal to secant squared. If none of these words, let's just turn them into sines and cosines and see what we can deal with then. Yep. That's what you did back in trig somewhere along the way, right? If you couldn't figure out how to prove something, you were like, how about sine and cosine? Let's see what happens then. Kind of the same deal again.
Thomas, would it be easier to do this immediately?
To turn into sines and cosines immediately. You could try. Okay. This one has secant to a power, which makes it kind of start to feel like step number 4. But it isn't. It's step 1, right? And these aren't really steps, guideline. It's guideline 1 because it's an even power. So guideline 4 really is, you go through them in order. If it doesn't work on 1, you go to 2. If it doesn't work on 2, you go to 3. We actually get it working right there on number 1. Guideline 1 works for this. So it says that we're going to have it, because we have a secant power that's even, we're going to save as secant squared, and then we're going to turn everything else into tangent. So let's take a look at trying that. So the first thing to do is to replace secant to the 6th with secant to the 4th and secant squared. And that secant squared will not change. That piece needs to remain the same. It's the secant to the fourth that needs to be manipulated.
Shouldn't that be 3x squared?
Oh, I left my 3 out. Yes, it should. Let's fix that. Thank you very much. All right. Okay, did I get everything okay then? Fabulous. All right, secant to the power 4. Well, if you take a look over here, the relationship between secant and tangent looks like this. Well, that's secant squared, though, and I have secant to the fourth, right? So if secant squared is 1 plus tangent squared, then secant to the fourth would be the same thing as taking what I just circled and putting a power 2 on each side. Agreed? Okay, that's what we're going to do. We're going to take this secant to the power 4, and we're going to rewrite this as 1 plus tangent squared of 3x, because that's our angle, squared. And this piece looks and feels a lot like the problem we did earlier, where we have to FOIL it out, right? And I'm trying to avoid having to write the steps to FOIL, so I'm just going to do it straight away. I square the first term. I multiply 1 times tangent squared, which would be tangent, and double it. So this is 2 tangent squared of 3x plus, and then I square the last term, which would be tangent to the fourth of 3x. And all of this is times secant squared of 3x dx. It looks and feels ugly, but it's about to change and become very clean very quickly. The whole point in turning them into tangents is that I can use U substitution. That's the goal. Okay? So with U substitution, what I want is I want my U to be the tangent of 3x. So what's the derivative of tangent? Secant squared, and then it's of the 3x dx, and I need one more thing.
1/3.
Is it 1/3 or 3?
Well, it'll be 1/3.
It'll be 3 on this side, 1/3 on the other side, which may be what you were wanting to tell me, like this.
1/3.
Okay, yeah, you guys are both right. Okay, look okay? All right, beautiful, beautiful things are about to happen, so I need probably more space for them to happen. Let me see if I can just write them down here at the bottom. Do I have another slide? I do. Excellent. Okay, so I have a 1/3. I have a 1 right here plus, what is the or what is the rest of it going to change into? 2u squared plus u to the fourth, and then du. There's no more secant at the end, right? Did I tell you it was going to turn into something so nice so fast? It really does. Okay, antiderivative time. What do you get?
U was for 1/3 equal U plus 2/3 U to the third plus 1/5 U to the third.
Yep, n plus c. But what was u? Careful. It was tangent of 3x, right? So this is 1/3 tangent 3x. I'm going to distribute the 1/3 while I work through it, okay? Plus 2/9 tangent cubed of 3x plus 1/15 tangent to the fifth of 3x plus c. The next one's even friendlier. I'm not joking, it really is friendlier, huh? Yeah, it's friendlier, it's cleaner. Okay, let's take a look. I've got secant to the fifth, I've got tangent to the third. I need you to identify which of the guidelines this is going to fall over. Fall under, not over, under. 2. Why, Nate?
Tangent's odd.
Tangent is odd and secant's not even, so we had to bypass 1, right? Yeah. Tangent's odd. So what does it say I'm supposed to do over here when tangent is odd? I'm going to supposed to save a secant tangent, right? And convert everything into secants. So I need one of these secants and one of these tangents to remain, and the rest of them will change. So the first one will be a secant to the fourth, and you'll notice on this one there's no angles that are doubled or tripled. Hang on, I'll show you. And the next one will be tangent squared, and then I want to save that secant x tangent x with my dx. This piece is going to be du eventually. Yep, I pulled a secant out, I pulled a tangent out. Okay, is everybody good with that? Pulled a secant out, pulled a tangent out. And the guideline says I'm supposed to change everything into what? Secants. So I need to make sure I don't change things that don't need to be changed. Like the secant to the power 4 is good. Leave it alone. Right? Don't mess with it. It's the tangent squared I want to change. So what is the relationship that will allow me, or what, not what is the relationship, but what will I change it to? Secant squared of x minus 1. Okay, so far so good. And then I can distribute through that, right? Right here. So I have the integral of secant to the 6th of x minus secant to the 4th of x. And I have secant x tangent x dx. That's as cleaned up as I want. Don't go distributing the secant tangent back through. That would be completely unhelpful, right? Our goal is to leave this alone so that it can be du eventually. So if that's supposed to be du, what would u be? Secant. Not a power, just secant. And the derivative of secant then is secant tangent. So secant x tangent x dx. So what does this become? With u to the 6th minus u to the 4th du. Did I tell you this one was nice and clean? Fewer steps than the last one. All right, what is u to the 6th antiderivative? 1/7 u to the 7th minus 1/5 u to the 5th plus a c. And we let u be secant. So this is 1/7 secant to the power 7 of x minus 1/5 secant to the power 5 of x plus c.
I like that one.
Like that one? Okay. One more in this little section. All right. We've gone through an example of number 1, an example of number 2. This one happens to be an example of which number?
4.
Yeah, it's 4. It's not 1 because it's odd, right? 1 was for evens. I'm skipping 3. You'll get to see it the same way that they work later with that one. But number 4 is a little bit different. It's kind of variation, so we're going to do an example number 4. Number 4 is going to be an integration by parts. It is telling you use integration by parts with dv equal to secant squared, which means that whatever else is there is going to have to be u, right? All right, so let's take a look. We've got v dv, I didn't mean that, u du, and then v dv, and they told me that dv has to be the secant squared of x dx. So what would u have to be? Secant of x. Okay, what's the derivative of secant x? Secant x tangent x dx. And what would v be? Tangent of x. All right, so this is u times v, which would be secant tangent minus v du. So v du is going to have a secant and a tangent squared, right? So tangent squared of x, secant of x, or in the other order, dx. And we've created something that doesn't look like what we originally started with, tangent squared secant, which means we have to go back to that list of guidelines and figure out how I'm going to integrate that one now. So, which of the guidelines will that fall under? Which one? 2? 1? I'm not looking at it either, so maybe we should all look at it together. It's not the first one because secant's not even. Is it the second one, tangent's odd? No. We don't want to do into 5. That would be not so very helpful. Well, is there any way to manipulate this using a formula that you know, relating tangent, secant? Oh, this just sounds complicated. Let's not do that.
You can take this tangent squared x and turn it into secant.
Okay, I think that's probably a good step for us. If we could change the tangent squared so that we don't have tangent in there anymore, we go back to only have secants in the problem, maybe we could go from there. And we know, and I've got all this mess down here, but we know that tangent squared is secant squared minus 1, right? So let's stick a little Fourier into that as our next step and see what happens. So the secant x, tangent x is at the beginning. Then I have minus the integral, and this is secant squared of x minus 1 times the secant of x dx. Okay, so can we manipulate this? Well, this is the integral of what?
It's going to be secant cubed of x minus secant of x.
Okay. Can I separate the integral into different pieces? Okay. So this is minus the integral of secant cubed of x dx, and then it'd be plus the integral, Evan sees something happening, of secant of x dx. Yeah, we had a trick like this last time. Y'all remember it? I actually have an equation here. We don't always think about it that way. In fact, we probably don't often think about it that way. But the integral of secant cubed is this thing that I have not yet solved for, correct? And when I get to this point and I recognize, oh my goodness, I have what I started at, that's actually a good thing. Because I could add that to the other side, and now I have 2 of them over there. So I can get rid of the fact that I couldn't deal with it very well by adding it to the other side. So this is 2 now, secant cubed of x dx equals. And I have to have some of the pieces still, or I have to write down the pieces that are still remaining. So secant x tangent x, and I've got plus the integral of secant of x dx. Okay, what is the antiderivative of secant of x dx?
Is that
Yeah, it's got a natural log. You guys have your antiderivative sheet there with you?
is that secant x supposed to be negative?
It's positive because we had a negative here and a negative here. Yep.
So it's tangent of secant.
Okay, it's natural log
Okay, antiderivative.
of the absolute value, yes.
Natural log of secant x plus tangent x. Plus
All right, that's what it is, yes. And I need to do one more step before I'm done. What's it going to be? Yeah, I need to divide by 2, right? So that gives me a 1/2 in front of each of these terms. And aside from the fact that I've got it kind of crammed in there, it's finished. So I've got 1/2 secant x tangent x plus 1/2 the natural log of the absolute value of secant x plus tangent x, and then plus c. I don't really need to put a 1/2 in front of the c. It's not technically wrong. It's just not necessary because c is a constant that could vary anyway as to whatever you've got going on in the problem, right? So it's not needed. Okay, we're good with this one? Got that trick in there. And at least Evan, because he kind of like that aha moment I heard it, saw the trick when it happened, right? So it did. It happened when we actually ended up with a cubed on both sides. Okay, one last set of of rules. I think this is the last one in this section. Yeah. These are product to sum formulas. And what these properties allow us to do is reconcile different angles. So if you have angles in the problem that don't match, this is where you go. Okay? So it's kind of like, I really view chapter 8 as like a game. So have you ever played, like Sudoku? There's rules, right? And you have to figure out which numbers go in the right boxes based on the rules of the game. Well, this is it. You look at what you have and you figure out which rules you have to apply because different properties are useful in different situations. So I can't just say, man, U substitution is the best thing ever because it just doesn't work for everything. Integration by parts, best thing ever. It doesn't work for everything either. So this is actually what we would do if we're going to reconcile different angles. So I have sine of A plus sine of B, and I can change them into a joint angle by doing a subtraction of the angles, addition of the angles, and you can see the formulas there. And the same thing happens whether I have sine and cosine, or cosine and cosine. Okay, so there's 3 different rules. All right, so if you take a look at this one, we know that we want to use this particular rule, if you will, because we have the sine and the cosine of different angles. If the angles match, it doesn't really help us. These rules just they aren't useful so much. But when the angles don't match, the rules are quite useful. Now, you might notice that one of the angles is negative. It's really not a big deal. I'll talk a little bit about even and odd powers, or not even and odd powers, even and odd angles in a minute. But we're just going to pretend like we don't care that it's negative because we really aren't going to care too much that it's negative in the end. So this one right here is the second one, it looks like, right? Because I've got a sine and a cosine in it. And I'm going to end up with a 1/2. I'm going to subtract the angles. I'm going to add the angles, and we're going to go from there. So I have an integral. I've got a 1/2 of the integral. I have sine of the angles subtracted. So this is negative 4x minus 3x. And then I'm going to do the angles added. It's plus the sine of negative 4x plus 3x. And do you have to actually write this step down? Well, no, but you're going to either write that one or the next one. At some point here, you're going to have this step next written down, which is the sine of negative 7x plus the sine of negative x
How'd you get plus?
dx.
Oh, is that
Are you okay, Abby?
plus? Yeah.
Okay. All right. I think on your trig sheet right now you have something that says something about even and odd functions. Do you have even and odd identities on there? Yes. It's the one right underneath Pythagorean identities. It tells you that if you have an angle that's negative inside of a sine, that it's equivalent to having the negative in front of the sine. And if you have a negative inside of a cosine, it's equivalent to not having the negative there at all. And it has to do with the fact that sine is an odd function and cosine is an even function. So either know which one's which or simply remember it's sine and tangent that are odd and cosecant. Sine, tangent, and cosecant are odd. And then cosine, cotangent, and secant are even. Those are the ones. Okay, so whatever it takes for you to remember which one's which. What's that? Maybe it's odd too. It is odd. No, you're right. That's right. Thinking about the graph of it, it's odd. Yeah, thank you. So the only ones that are even, that might be the easiest way to remember that. The only ones that are even are cosine and secant. Did I say that right, Evan? Okay. Okay, if it's odd, if it's an odd function, it means that the negative can come out in front. So we can deal with it right here. I'll show you how we could have dealt with it at the beginning as well if you'd like. But this means I have a negative 1/2, or a 1/2. And I've got the integral of negative sine of 7x minus the sine of x dx. You could pull it out in front if you don't like them there at all. You could put negative 1/2 the integral of sine of 7x plus the sine of x dx. Okay then, what in the world is the antiderivative of sine? Cosine or negative cosine? It's negative cosine.
What antiderivative?
Yeah, antiderivative. And I get the 7x. What am I missing? The 1/7. So I have negative 1/7 cosine 7x. And then I've got another sine here, right? So this is another cosine, but I don't have to worry about, it's negative cosine. I don't have to worry about the fraction in front. Why? Yeah, the angle's just x. Yeah? So this negative 1/2 distributed through gives me a 1/14 cosine of 7x plus cosine of x plus c. Oh, there's my 1/2 missing. I knew I didn't have a negative, but there is a 1/2. Yes, thank you. If you had wanted to, if you had noticed it right here, you could have dealt with the negative right here. Okay? So if you had dealt with it at the beginning, of course you'll still get the same answer, but your integral would have looked like the negative in front, and then you would have had sine of 4x cosine of 3x dx. Again, when you subtract the angles, you're going to get one of them as x. When you add the angles, you're going to get one of them as 7x. You get the same thing resulting from that. Okay? So either place that you notice and want to deal with a negative is fine. All right.